Okay, we're here today to talk about displacement, velocity, and acceleration, and to think about them in ways that we don't usually think about them. To expand on what you may have introductorily, that's such a word, learned in a high school physics course, let's say. Now, usually when we teach and learn the kinematic equations, which at this point you've probably seen and used, we do it in somewhat the following order. We learn about displacement first, then velocity, and then acceleration. So early on, you probably use this equation, x equals x sub 0 plus v sub 0 t plus 1 half at squared, to find acceleration. This is, by the way, once you've gotten into accelerated motion. You would have started with constant velocity motion, but maybe within the first few weeks you would have talked about an accelerated motion. And at the time that you used this equation, you probably assumed, well, it just fell out of the sky, or the teacher gave it to me and it just works. Or maybe they did experiments and come up with this equation, which, by the way, you can do. And you also use this equation, v equals v sub 0 plus at. But neither one of these equations can just fall out of the sky. And it's not really acceptable to just come up with things by equations by experimentation without a theoretical agreement. And there actually is a way to theoretically come up with these equations. And that's part of what I want them here to show you today. Now, this order that I've got these does show that each equation is a derivative of the previous one. Well, there's only two here. But if you know a little bit about a derivative, if I take the geometric derivative of 1 half at squared dx dt, multiply the 2 over here times the 1 half, you get 1, and it drops to at. And if you took the derivative of this, the v sub 0 would, or the t would drop off. And this being a constant, it would just drop off. So this equation, the second equation, is a derivative of the first one. And I could take the derivative of this equation and just get a. But this is not the natural progression of the universe. You don't start with, you may presume that you do since you learn it this way, but you don't start with the position equation and then find velocity from that and then find acceleration. Not in the universe you don't. Now maybe in your physics class you do, but that's not the way that's actually done. And a question does come up on rare occasions is, where does this half come from? A couple of times in my career I've had a student ask this. I think I've always led to them to that question, but I remember when I was in high school seeing this equation and asking my high school physics teacher, okay, where does that half come from? Okay. His answer was something like, well, it just is there. Now, that's not an acceptable answer. It wasn't that proficient, I don't think it is, in its occupation, actually. So how do these equations come up? Well, nature comes up with these equations, actually, in what we would consider the reverse order. The way we learn them is actually backwards. What we start with, what nature starts with, is gravity. The universe, at least in regards to kinematics, starts with gravity, which is an acceleration. Try not to think of gravity as a force. It's always taught this way, but that thinking will get you in trouble. You're much more likely to understand what's going on if you think of gravity as an acceleration. Now, how gravity is made, let's not worry about. That's way beyond the scope of this discussion, and there's experts that are continually working on that. But what we can do is describe gravity once it's made. So we'll pretend we're kind of in Isaac Newton's day or in the 100 years following, and we really have no idea how this gravity originates, but we do know what it does. So gravity sources make gravity. And as a body experiences that acceleration, what we can do is run the math and let the math dictate through an integration, an equation that expresses the velocity with respect to time. So gravity happens, and the object moves, and its velocity changes. And the velocity you have at any moment is the velocity you end up with, let's say, is equal to the integral of the acceleration dt. In other words, graphically looking at this, we are going to find the velocity by finding how much under this curve we're using. So it's the length times width, the area under this curve. Now, because it's just length times width, we can do that. But if it was not a constant acceleration or something else, we would have to integrate. So it works for a linear equation, it works with an integration, but the integration describes it for all cases. So when you integrate, take velocity is equal to the integral of a dt, you end up with v equals at plus c. This is what math people would say you get. It turns out that constant, don't forget your c, I used to do that all the time, constant that you get is actually the original velocity that you started with. And so, by the way, it works when the original velocity is not zero, as well as when the original velocity is zero. But we're going to look at cases where the velocity is zero because that's easier. Now, so this is what the math people would come up with. When you're in physics class, this is the equation that we're given that falls out of the sky. The only difference between these two is you've interchanged the position of the v sub 0 and the at. So the equation doesn't fall out of the sky. It's the result of basically integrating gravity. Nifty. Remember, gravity, think of it as an acceleration. Now, if we take this velocity that we resulted and we integrate that, the mathematics of the motion dictates that we will get the displacement equation with respect to time. And we will see this 1/2 appear mathematically, by the way. So if I want to find okay, let's take it. Ooh. Okay, we're back. So if I take this velocity part and I integrate it here to find the displacement. In other words, what I would be doing there would be trying to find the area under the velocity graph here so I could plot the displacement. You probably did the reverse of that in a lab in your high school physics course at some point, probably pretty early on in the first month or two. But when we integrate v right here, that's this part, so I can make the substitution right here. Actually, what I've done is this one. Here's what you look at in physics class. Here's what you do in math. So I'm going to write it the math way. So the integral of velocity dt is the integral of at plus original velocity dt, quantity, all that's quantity. And when I take the integral of that, I get 1/2 at squared plus v sub 0 t. Don't forget plus your c. Now if I rewrite that over here, that original c, it turns out, is just the original displacement, which we're usually going to consider to be 0. Like this, starting down here at 0. But it doesn't have to be. It also works when x is not 0. There's 0, and there's where your starting x is. We're not going to try to crunch numbers on that part, but it does work when x is not 0. Now, that's what math people come up with. If you reorganize it this way, by moving x sub 0 over here and 1/2 at squared over here, this is your math. This is the physics equation you get, and your 1/2 notice shows up right here. That's where that 1/2 comes from. It's a result of a double integral of gravity, strangely enough. Well, that may seem a bit technical, so let me give it to you maybe in a way that you're It's a little more layman's terms. If you want to get the velocity, what you can do is just find the area under the AT curve. And if you want your velocity at some particular time t, you just calculate the area under there, and that'll give you this data point for the velocity t. Okay. What about if you want the displacement? Well, the area under this velocity graph will give you the displacement. Area equals displacement. Well, the area under here is 1/2 base times height because we've got a triangle. Okay? And base is time, the height is velocity. I've got them reversed over here, so I've got 1/2 height times base. So we end up with 1/2 dt, which looks familiar to us. Now, here's where you got to be a little creative. If you take that original AT that you found back here, A times T, and you put it in for B, we can put A times T in for B. So that's what it is. Put that in there, and we've got then x equals 1/2 A times T times the original T, or x equals 1/2 AT squared. Now, what happened to my x sub 0? Well, in that case, I'm starting at 0, so it's there. What happened to my v sub 0? Well, in this case, I'm starting down in the corner. It's at 0, so it's there. It's not present to look at because we don't need it. Just pointing out, this also works if v is not 0. And it also works if the starting position is not 0. It's just a little more complicated. Okay, lastly, I want to point out some things that are assumptions we make that are wrong when we're teaching and learning velocity, acceleration, and position, or displacement. It's important to realize that all of this previous work was done in the context of a constant acceleration, which is usually the case for instruction. But this is very deceptive, because in real life, constant acceleration is a fairly unusual occurrence. Even falling objects, if you do a lab where you go out and drop something or throw something, they don't have constant accelerations, although sometimes they're close in lab. The accelerations are only fairly close to constant if the objects aren't receiving significant drag from the atmospheric friction. So you're probably dropping something in the lab, it's not going to get going real fast, it's going to have a high enough density. You try doing that lab with a paper wad, it's not going to work very easily anyway. Also, it only works if the falling distance is too small for changes to account for changes in the gravity as they get closer to the source of gravity. So if you're dropping something several meters, let's say on Earth, it works. If you're dropping something dozens of kilometers, it won't work because your gravity starts to not stay constant. It would be just a smidge less, let's say 100 kilometers up than it is right at the surface. So even a car accelerating is almost never a constant acceleration unless it's not going very far or very fast. Now, all of that said, all of the previous work we've done is still valid for accelerations that aren't constant. It's just that the work in the mathematics gets far more complex. You're stepping into the world of double and triple integrals and differential equations to do that. So we usually don't do that, and neither do I when I'm instructing. Unfortunately, that deceives the learners into thinking that constant accelerations are the norm, where in reality, constant accelerations are pretty rare. So, a little more detail on stuff you should already know some things about. Hope you enjoyed it.